Okay, so in the last class, we discussed about evaluation of properties like change in internal energy, change in enthalpy, uh, change in entropy, as well as heat transfer and work done for all the five process. It is a constant for for constant volume, constant pressure, uh, isothermal, reversible adiabatic, and polytropic process. In today's class, we will discuss about ideal gas mixtures. The first one, in the ideal gas mixture, we have taken mass fraction. Okay, so the mass of the mixture, suppose if there are more than one gases, okay, then the total mass of the mixture will be is a sum of masses of the individual components. Okay, that is m suffix m. Okay, here m stands for mass and small m suffix represents mixture. Okay, so the total mass of the mixture will be equal to m1 plus m2 plus m3, okay, plus dash dash, okay, depending on the number of gas. Okay, so many components of masses of the gases will be added to get the total mass of the mixture. Okay, for example, if there are two gas, okay, and gas 1 is having mass 2, whereas gas 2 is having mass 3, then 2 plus 3 will be 5. That is the total mass of the mixture of the gas of the two gases. Okay, likewise, uh, we can write the total mass of the mixture of gases for I equal to 1 up to k components of gas. Next, okay, mass fraction. It is defined as a ratio of mass of a component to the mass of the mixture. That is known as mass fraction. Okay, that means okay, what is the mass of the individual gas divided by total mass of the mixture of the gas. As I told you, if there are more than one gas, okay, so what is the mass fraction of the particular gas 1 if you take, and is m1 by, so if there are two gases, you have to take mass of the mixture will be m1 plus m2, right? Now if you divide the equation 1 by total mass of the mixture of the gas, okay, then what you are going to get, okay, left hand side m divided by mm will be 1. That will be equal to m1 by mm plus m2 by mm plus m3 by mm plus so on. So m1 by mm represents mass fraction of gas 1. mf2 represent mass fraction of gas 2. Okay, similarly mf3. So here mf1, mf2, mf3 are called as mass fractions. Okay, so obviously the sum of the individual mass fractions in a mixture will be equal to 1. That is what here. Okay, here left hand side there is a 1. So suppose if there are only 3 gases, then mf1 plus mf2 plus mf3 will be equal to 1. If there are only 2 gas, mf1 plus mf2 will be equal to 1. That is a meaning. Next, mole fraction. So similarly, what we have defined for mass fraction, similarly we also defined for mole fraction. Okay, so the mole number of the mixture is nothing but the sum of mole numbers of the individual components. Okay, here I have shown you the example. Okay, hydrogen plus oxygen. Okay, hydrogen is having a 3 kg moles, oxygen is having 1 kg mole. Okay, when you add these two gases, what is the total number of moles? It is 4 kg moles. Okay, so nm number of moles of the mixture will be 4 kg moles if there are only two gas n1 plus n2, right? So mole fraction is nothing but the ratio of mole number of a component to the mole number of the mixture. It is represented by the y. Okay, mole fraction is represented by Y, okay, suffix I represents individual component. So Yi will be Ni by Nm. Yi will be Ni by Nm. Okay, it's nothing but number of moles of the individual component. Individual component means individual gas. The total number of moles of the mixture. So here, okay, if I want to find what is a mole fraction of hydrogen, okay, it is nothing but what is Ni? Number of moles of the individual. It is 3. What is the Nm? Here it is 4. 3 by 4 will be 0.75. Okay. Similarly, if you want to find what is a mole fraction for oxygen, it is 1. 1 is represents individual number of moles. Individual component number of moles is 1, and total number of moles is 4. 1 divided by 4 is equal to 0.25. So when you add this number of moles, you are going to get 1. Okay. So here same way we have divided the equation 2 by Nm. So left hand side Nm will become 1, will be equal to N1 by Nm plus N2 by Nm plus N3 by Nm plus so on, depending on the number of moles fraction of the gas. Okay. So that will be equal to Y1 plus Y2 plus Y3. Okay. Y1 is nothing but N1 by Nm. Y, I told you Y represents mole fraction. Okay, Y1, Y2, Y3 are the mole fraction. Obviously, the sum of individual mole fraction in a mixture will be equal to unity, just like mass fraction. So, mass fraction is represented by MF, whereas mole fraction is represented by Y. Okay. Small equations. Okay, we know that mass is nothing but number of moles into molecular, because we have already defined what is number of moles is nothing but mass by molecular mass. So m will be equal to n into mu, right? Next, the average molecular mass or the molar mass of the mixture is given by, okay, so how will you find the average molecular mass? It is nothing but, okay, you know m is equal to n into mu, so mu will be m by n. Okay, and you need to find what is the molecular mass of the mixture. Then we have added suffix m. Okay, so mu m will be equal to mm divided by nm. Okay, how will you find the total mass of the mixture? Is nothing but summation of all the mass of the individual components divided by nm. Okay, what is how will you find mi? Either you can go for m1 plus m2 plus m3, or if you know n and mu, then it is nothing but summation. Okay, because m is equal to n into mu, so it is nothing but summation of ni into mu I divided by nm. Understood? How you got this? Because m is equal to n into mu. Also, you know mi is not summation of mi is nothing but m1 plus m2 plus m3, or I also in terms of number of moles and molecular mass, I can write m is equal to n into mu. That is what I have written here. So n into mu, that is nothing but m of the individual component, right? You know that ni by nm. What is ni by nm? It is nothing but mole fraction, no? Huh? So ni by nm is nothing but mole fraction. That is what y, okay, of the individual component into mu I, as it is I have written here. Understood how you got this equation? Where I will be equal to 1 up to k number of components. Okay, some k number of components. So molecular mass is nothing but summation of y, that is the mole fraction of the individual component multiplied by the molecular mass of that individual component. Once you got molecular mass, how will you find the characteristic gas constant of the mixture? You know that R is nothing but R bar by mu. General, what is the general equation for characteristic gas constant? Is nothing but R bar by mu. Okay, and R bar, whether it is an individual gas component or a mixture of gas component, that R bar will remain same, because it's a universal gas constant. I told you it doesn't vary, whereas only the characteristic gas constant will vary depending on the gas. Okay, so Rm will be R bar by mu m. Mu m is nothing but molecular mass of the mixture you have calculated using this mole fraction and molecular mass of the individual component. So you can substitute in this and you can get the value of characteristic gas constant of the mixture. Okay, this will be required while doing numericals. Next, Dalton's law of partial pressure. Okay, so it states that the pressure of a gas mixture is equal to sum of partial pressures of each gas would exert if it existed alone at the mixture temperature and volume. Okay, suppose if there are two gas, that is uh, gas A and gas B having partial pressures of PA and PB, then total pressure will be summation of partial pressures of the individual gas. Okay, that is nothing but PA plus PB. But you should remember that during Dalton's law of partial pressure, volume and temperature of gases, okay, individual gases will be same, as well as even the mixture. When you combine these two gases, the volume and temperature also remains same. Okay, so total pressure will be sum of partial pressures of the individual gas. Suppose if there are three gases, then okay, total pressure will be PA plus PB plus PC. Okay, whereas gas is C, volume and temperature is same like gas A or gas B or gas mixture. Okay, it will be the same. So this I have taken from Yunus book. Next, Avogadro's law of additive volumes. Okay, the volume of a gas of a mixture will be equal to sum of the volume of each gas would occupy it if it existed alone at the mixture temperature and pressure. Okay, here pressure and temperature will remain same of the individual gas as well as the gas mixture, but the volume, when you take total volume, it is given by sum of partial volumes of the individual gases. Okay, here gas, there are two gases, gas A and gas B. Both are at the same pressure and temperature. Okay, but the volumes are different. VA and VB is the volume occupied by gas A and gas B respectively. So when you mix together, the pressure and temperature also remains same like individual gases, but the total volume will be sum of individual volumes of the gas, that is Va plus Vb. This is known as Avogadro's law of additive volumes. Okay, next, so relation between partial pressure, mole fraction and volume fraction. Okay, so here I have written the equation for the gas mixture. Okay, that is nothing but ideal gas equation. You know that ideal gas equation is given by PV is equal to MRT. Okay, PMV is equal to MMRMT. Okay, this you know. Okay, here I am using this equation because I will apply Dalton's law of partial pressure. Okay, volume and temperature will be same. Whether it is for Dalton's law of partial pressure, whether it is individual gas or a gas mixture, volume and temperature will remain. Volume and temperature will remain same. So I have written suffix m for pressure, mass, and as well as characteristic gas constant. So next, you know that mass. Okay, n. What is n? N is nothing but m by mu. So what is m? N into mu. Correct? Number of moles. What is n? Number of moles is nothing but mass by molecular mass. What is m? M is nothing but n into mu. This you know from definition of kg moles. Number of kg moles. N is nothing but m by mu, or m is equal to n into mu of the mixture Rm into T. And you know that mu into R, molecular mass, into characteristic gas constant represents universal gas constant, that is R bar. Nm R bar T. This is for the gas mixture. Okay, now I am going to write the ideal gas equation for the individual gas component. So it's nothing but Pi Vi is equal to Mi Rit. Okay, so Vi T, that is be equal to what? Again, M is nothing but N into mu for the individual component. Mu into R represents R bar. So Ni R bar T. This is for individual component. Okay, we have taken the ratios of 2 and 1. Okay, if you just taken the ratios of equation 2 and equation 1, here PMV ಇದೆ PIVI ಇದೆ PIVI by PMV ಇದೆ. You know, according to Dalton's law of partial pressure, volume of the individual gas as well as volume of the mixture ಇಲ್ಲಿ VM ಅಂತ ಬರಿಬೇಕಿತ್ತು. Okay, so V suffix M, volume of the individual component and volume of the mixture will remain same. That is why both volumes gets cancels. What is remaining? Pi by Pm is equal to, ಇಲ್ಲಿ ನೋಡಿ, ಇಲ್ಲಿ ಎನ್ ಎಂ ಆರ್ ಬಾರ್ ಟಿ ಇದೆ, ಇಲ್ಲಿ ಎನ್ ಐ ಆರ್ ಬಾರ್ ಟಿ ಇದೆ. ಎನ್ ಐ ಆರ್ ಬಾರ್ ಟಿ ಡಿವೈಡೆಡ್ ಬೈ ಎನ್ ಎಂ ಆರ್ ಬಾರ್ ಟಿ. ಆರ್ ಬಾರ್ ಟಿ gets cancels, so it will be just Ni by Nm. So the ratios of our pressure fraction will be equal to mole fraction. Pressure fraction is equal to mole fraction. How you got? You have applied Dalton's law and you have got this. Okay, next we are going to apply Avogadro's law of additive volumes. Okay, as usual we have written the ideal gas equation for individual component, that is PMVI is equal to Mi Rit. You know, for according to Avogadro's law, pressure and temperature for an individual component as well as for the gas mixture, it will remain same, pressure and temperature, only the volume gets additive. Okay, so ಇಲ್ಲಿ Mi Rit ಇದೆ, as usual M is nothing but N into mu, or it will be Ni R bar T. Like as usual you have got equation 2, that is what equation 4. Only thing is ಇಲ್ಲಿ ಓಕೆ ಇಲ್ಲಿ ಪಿ ಐ ಬರಬೇಕಿತ್ತು. ಓಕೆ, so just you take equation 4 divided by equation 1, what you are going to get? Okay, ಇಲ್ಲಿ okay, pressures, whether it is individual component or mixture, it will remain same. Pm gets cancels, Vi by Vm. ಓಕೆ, ಇಲ್ಲಿ ವಿ ಎಮ್ ಅಂತ ಹೇಳಿದ್ದೆ, ಇಲ್ಲಿ ವಿ ಎಮ್ ಹಾಕಿದ್ರೆ ಅವಾಗ ವಿ ಐ ಬೈ ವಿ ಎಮ್ ಬರುತ್ತೆ, ಈಸ್ ಈಕ್ವಲ್ ಟು ಎನ್ ಐ ಬೈ ಎನ್ ಎಮ್ ಬರುತ್ತೆ. ಅಂಡರ್ಸ್ಟೂಡ್? ಓಕೆ, ಇದು ಆಕ್ಚುಲಿ ಪಿ ಐ ಬರಬೇಕಿತ್ತು. ಓಕೆ, ದಿಸ್ ಇಸ್ ಪಿ ಐ. ಓಕೆ, ಯು ನೋ ದಟ್ according to Avogadro's law, okay, pressure and temperature, whether it is individual component or mixture, it will remain same. So pressure gets cancels, it will be Vi by Vm is equal to Ni by Nm. So if you just compare the equations 3 and 5, the pressure fraction is also equal to volume fraction, that is also equal to mole fraction. Mole fraction is represented by Y. Next, we'll try to obtain characteristic gas constant in terms of mass fraction. This is very simple. So let us consider two gases, gas A and gas B, contained in a vessel having volume V and temperature T. Okay, so there is a vessel which is having volume V and temperature T, and in this vessel there is a two gases, gas A and gas B. Okay, we'll write down the ideal gas equation for gas A. PAV is equal to MA RAT, because volume and temperature, whether it is for gas A or gas B, it remains same. Okay, and PBV is equal to MB RBT. So when you add these two equations, what you are going to get? PA plus PB into V. Okay, PAV plus PBV is nothing but PA plus PB into V is equal to MA RA plus MB RB. Okay, temperature you can take it outside the brackets. When you add right hand sides, okay, temperature is common, you can take it outside the brackets. uh, Next, according to Dalton's law of partial pressure, okay, you know that sum of partial pressures of the individual gas is nothing but partial pressure of the mixture. It is Pm into V. Okay, Pa plus Pb I have written as Pm into V as it is. Okay, right hand side I have written as it is. Okay, that is equation 1. Next, if you write down the ideal gas equation for a mixture, PMV, okay, Pm is a partial pressure of the mixture. Volume and temperature is same. Okay, I told you no. Volume and temperatures, both the gas A and B are having volume and temperature to be same in the gas in the mixture. So it is V. Okay, mass of the mixture MM. Okay, it is then into Rm into T. Okay, characteristic gas constant of the mixture into temperature T. Okay, volume and temperature remains same for the mixture and as well as for the individual gas. Right. When you compare this equation 1 and 2, left hand sides are equal. You can equate right hand sides. So you can equate right hand side. What you are going to get? Okay, MM is equal to MERA into MBRB. Temperatures on both the sides gets cancels. And finally, what is RM? Okay, is nothing but characteristic gas constant of the mixture is nothing but MERA by MM plus MBRB by MM. Here mass of the individual component is gas A divided by the mass of the mixture is nothing but mass fraction of gas A, and similarly MB by MM represents mass fraction of gas B. Okay, so it is RM will be MFA RA plus MFB RB. Okay, this is how you are going to obtain the characteristic gas constant of the mixture when you know the mass fraction. Okay, so coming to the numericals. So in this, consider a gas mixture that consists of 3 kg of, okay, this is O2 oxygen, actually it is oxygen, 5 kg of nitrogen and 12 kg of methane CH4. Okay, this should have been suffix. Okay, O2 represents oxygen, N2 represents nitrogen and 12 kg of methane CH4. Determine mass fraction of each component, mole fraction of each component, and average molar mass and gas constant of the mixture. Okay, they have given the masses of the three. There are three gas: oxygen, nitrogen, and methane. CH4. Okay, so there are three gases. They have given the masses of the three gas. How will you find the total mass? Just add all the mass of the individual gas, that is oxygen plus nitrogen plus CH4. You are going to get 20 kg. Then how mass fraction is very simple. Okay, you know mass of the individual gas divided by the mass of the mixture. Mass of the oxygen is 3 by 20. Okay, 0.15. Similarly for nitrogen and CH4 you do it. Okay, you're going to get the values. Next, to find the mole fraction, we need to determine the number of moles of each component. Okay, how will you do it this? Okay, you know number of moles, how we have defined number of moles is nothing but mass divided by the molecular mass. Mass divided by the molecular mass. Okay, mass of the oxygen is 3 and molecular mass of the molecular mass of oxygen is 32. So 3 by 32 is equal to 0.094 kg moles. Okay, ಇಲ್ಲಿ ಇದು ಸಫಿಕ್ಸ್ ಎಮ್ ಇರ್ಕೂಡ್ದಾಗಿತ್ತು. ಓಕೆ, this suffix m should have been cancelled. Okay, next, number of moles of nitrogen. is nothing but mass of nitrogen divided by molecular mass of nitrogen. Similarly for CH4. Okay, if you just calculate what is the number of moles for oxygen, mass of the oxygen is 3 and molecular mass is 32. Okay, I told you know you have to remember the standard values of molecular mass of standard gases. Okay, next nitrogen it is 28, for CH4 it is 16. Hmm? Okay, just calculate, you're going to get the values. Then total number of moles, you have to add all these three values. You're going to get the total number 0.094 plus 0.179 plus 0.75. You're going to get 1.023 kg moles. Once you got this, then you can find what is a mole fraction. 0.094 divided by 1.023, you're going to get this. Similarly for nitrogen, okay, 0.179 divided by the total number of moles of the mixture is 1.023, you're going to get the value 0.175. Similarly for CH4. Okay. Now, how will you calculate average molecular mass or molecular mass of the mixture? Is nothing but total mass of the mixture divided by number of moles of the mixture. Okay, total mass of the mixture, how we have calculated now, it is 20. And total number of moles of the mixture is 1.023. Just simplify, you're going to get 19.6. Okay, kg per kg mole. You know the unit for molecular mass is kg per kg mole. Once you got molecular mass of the mixture, you can also calculate what is the characteristic gas constant of the mixture using the equation R bar by mu m. So it is nothing but 8.314 divided by 19.6. You are going to get 0.424 kilojoules per kg Kelvin. Okay. So this is how you are going to find the values. Okay. Just you should know the mass fraction, mole fraction equations. Okay. Next problem. There is a rigid vessel which contains 1 kg of nitrogen at 1.8 megapascal pressure and 300 Kelvin temperature. The pressure is required to be raised to 2.5 megapascal, and this is achieved by adding oxygen. Determine the mass of oxygen added if the temperature is presumed to remain constant. So there is a rigid vessel, okay, which contains 1 kg of nitrogen at 1.8 megapascal and 300 Kelvin temperature. Okay, they have given the pressure and temperature of the nitrogen. The pressure is required to rise to 2.5 megapascal. Is achieved by adding oxygen. You are going to add oxygen and the pressure will be raised to 2.5. So you are determining what is the mass of oxygen added if the temperature is assumed to remain constant. Okay. First, we'll find what is the number of moles of nitrogen. How will you find number of moles of nitrogen? You know mass by molecular mass. Okay. So mass of nitrogen is 1. Molecular mass of nitrogen is 28. It will be 0.0357 kg moles. Next, partial pressure of nitrogen is 1.8 megapascal. Okay. And the partial pressure of oxygen in the mixture will be, how will you calculate? You know what is the total pressure? 2.5 minus 1.8 will give you what is the partial pressure of the oxygen. You apply Dalton's law, okay. So total pressure is 2.5 and the nitrogen pressure is 1.8. Okay, so the difference will give you what is the partial pressure of the oxygen in the mixture. Okay, that is 0.7 megapascal. And next we have applied pressure fraction is also equal to mole fraction. Okay, mole fraction. So PO2 by PN2 is equal to NO2 by NN2. So number of moles of oxygen is nothing but pressure of the partial pressure of oxygen multiplied by number of moles of nitrogen divided by partial pressure of nitrogen. Here partial pressure of oxygen you have calculated 0.7. Okay, and number of moles of nitrogen is how much? Number of moles of nitrogen you have calculated 0.0357 divided by partial pressure of nitrogen how much? That is also 1.8. Okay, here ಇಲ್ಲಿ 10 power 6 ಹಾಕಬೇಕಿತ್ತು. ಪಾರ್ಷಿಯಲ್ ಪ್ರೆಷರ್ ಆಫ್ ಆಕ್ಸಿಜನ್ 0.7 megapascal ಇದೆ ಇಂಟು 10 power 6. ಇಲ್ಲೂ ಕೂಡ ಇಂಟು 10 power 6 ಡಿನಾಮಿನೇಟರ್ಲಿ 10 power 6 10 power 6 cancels. Okay, so the number of moles of oxygen will be 0.01388 kg moles. Okay, once you got number of moles, how will you find the mass? Mass is nothing but n into mu. Okay, n into mu, a number of moles of oxygen into molecular mass. Okay, multiply, you are going to get 0.443 kg. Number of moles of oxygen is nothing but just now you have found, and the molecular mass of oxygen is 32. Okay, you have to remember this. For some standard gas, you have to remember the molecular mass. Okay, and you can obtain the mass of oxygen. Okay, this completes numericals. So next is MCQ. Okay, first one, what is the partial volume of gas in a mixture? Is a volume occupied by single gas alone of a mixture at the same temperature and pressure of the mixture, or it is total volume of the mixture at a certain pressure, or both A and B and none of the above. Okay, if you see what is the partial volume of the gas in a mixture, you have to apply Avogadro's law of additive volume. What it says, a volume occupied by single gas at the same temperature and pressure of the, that is a partial volume of gas in the mixture. Okay, so it is correct answer is A. Next, the sum of partial volumes of all gas in a mixture is equal to total volume of the mixture, that is B. Again, Avogadro's law of additive volumes. Total volume is nothing but sum of partial volumes of gas in the mixture. So in today's class, you learnt about ideal gas mixtures, that is mass fraction, mole fraction, and how to obtain the characteristic gas constant for a mixture in terms of molecular mass and the mole fraction. Next, you have obtained the relationship between pressure fraction, volume fraction, and the mole fraction, and also you have derived the equation for characteristic gas constant of a mixture in terms of mass fraction. Okay, thank you.